Welcome to Lesson 6 of Module 3 on Transfer Learning. We'll begin with an introduction to transfer learning and its advantages. We will then cover the steps of transfer learning and using pre-trained models. Transfer learning is a popular process to transfer the knowledge that is learned while solving one problem to a new problem. The process has two main datasets: the source dataset, which is the original dataset used to train the model, and the target dataset, which corresponds to the new problem. Typically, the source dataset is larger or more general than the target dataset. This allows the model to leverage the knowledge gained from the larger source dataset and apply it to the specific target task, often leading to better performance and faster convergence compared to training from scratch on the smaller target dataset alone. Here is an example of transfer learning, where a pre-trained convolutional neural network model, such as AlexNet, is used to train a cat classifier. The process involves taking a CNN model that was previously trained on the ImageNet dataset, which consists of 1.3 million images across 1,000 classes. The weights of this pre-trained model are kept, and it is then retrained on a smaller cat dataset containing 10,000 images with only two classes, cat and not cat. This allows the model to leverage the knowledge it has already learned from the larger ImageNet dataset and apply it to the more specific task of classifying images as either containing a cat or not. Transfer learning offers significant advantages in terms of efficiency. Knowledge transfer happens through the reuse of weights and the model architecture that came from training on the source dataset. Training models from scratch on large source datasets is expensive and time-consuming. With transfer learning, you can download a pre-trained model as the starting point, leveraging the knowledge it has already learned. Many of these pre-trained models are publicly available, allowing you to save time and computational resources. Transfer learning produces high-quality models. The models that are trained on large source datasets learn universal feature representations well. These models learn how to handle many images from many categories. These learned universal representations are passed to the model that is trained with the target dataset through the refinement of the prior weights. The transfer learning process has four main steps. The first step is to get a pre-trained model, or pre-train it on the source dataset. Many pre-trained models are available to download. The second step is to create a target network and copy the trained parameters. The third step is to create and randomly initialize the output layer. Example: recall the cat classifier example. The original model has 1,000 classes, which means it will have 1,000 outputs. The target problem has only two classes. In this step, the last layer is initialized as an output layer with two outputs. The fourth step is to train the network. The weights of each layer of the pre-trained network, excluding the output layer, are copied into the target model weights. The hidden layers of the target model are now identical to the hidden layers of the pre-trained source model. The weights of the output layer of the target model are initialized randomly, or using a form of weight initialization. The target model is now trained on the target dataset. During training, the weights of the output layer are trained from scratch, and the pre-trained weights in the hidden layers are fine-tuned to specialize to the dataset. Here is a review of the transfer learning steps. First, we need to obtain a pre-trained model or train a model on a source dataset. Next, we create a target neural network architecture and copy the trained parameters from the pre-trained model. The output layer is then created and randomly initialized, as it needs to be trained specifically for the new target task. Finally, we train the output layer from scratch and fine-tune the rest of the transferred layers on the target data. Usually, training under transfer learning conditions is done with strong regularization, such as a smaller learning rate and fewer epochs. The more samples that are in the source dataset, the better it can prepare the model for different use cases. It's important to be familiar with the pre-trained models that are available because they each have different properties. Pre-training is usually expensive. A common practice is to download a previously trained model and use it for transfer learning. The Torch Vision package provides pre-trained models for different computer vision problems for image classification, object detection, and semantic segmentation. This table compares the performance of various pre-trained models from the Torch Vision package on the ImageNet dataset. The ResNet and ConvNext models generally outperform AlexNet, with the larger models achieving higher accuracy but also having more weights. The ConvNext large model achieves the highest top 5 accuracy of 97.0%, but has the most weights, at 197.8 million. You can use a pre-trained model in multiple ways, ordered from least costly to most costly. The first option is to use the pre-trained model as is, without any further training, which is the least computationally expensive method. The second approach involves training only the last layer of the model, while keeping the other pre-trained feature layers frozen. The third method is fine-tuning, where all layers of the pre-trained model are retrained end-to-end on the target dataset. Finally, the most costly option is to train the model from scratch using the target dataset, without leveraging any pre-trained weights. These methods offer a trade-off between computational cost and potential performance gains, allowing practitioners to choose the appropriate approach based on their requirements and available resources. Thank you.